So this video, I want to kind of use Excel to work out some examples in 5.3. So again, we're working with normal distribution, but this time, instead of looking for the area of the area of the curve is given. What we're looking for is going to be the z-score or the x value itself. So question 3 from your homework says find the indicated z-score shown from the graph to the right. So to do this problem in Excel, what we need is the cumulative area to the left. So we're going to need this area over here to do the cumulative area on Excel. So there's not a right side on this like we can kind of do sometimes. Uh, we're going to have to use the area to left since that's the way it's kind of programmed to do is cumulative area. So to find the cumulative area to the left, we have to remember the area of the curve is 1, so we have to go 1 minus this 0.0505. So what I can do over in Excel is to find the z value, we can go here, we can hit equals, and we can kind of go 1 minus, and then we got B2 there. And that'll give me this 0.9495. Now, we can use this value to find the z-score. So just like on the calculator, we use what's called inverse normal. But here we actually type in equal sign and we type in norm and we do norm dot inverse. So if I double click that, that'll give me my field. So it needs a probability, the mean, and the standard deviation. So since we're dealing with z-scores, the probability is going to be the area in the curve, which was the 0.9495, so it's going to be B3. And then the mean, I didn't put that up here, but we'll just type in 0 for the mean. And then the standard deviation was 1. So we can just close our parenthesis off there, hit enter, and that'll give us our z-score of 1.640025. But if we round to two decimal places, that's going to be 1.64. So remember, if you go left to z-score, if you go left to 0, the z-score should have been negative. If we go right of 0, the z-score should be positive. So that looks like it's kind of about right there. So feeling pretty good about that answer. Uh, so the next example is find the indicated z-scores. So notice how we have the area between uh, in the middle this time, in the center, if you will. Now, what I really need is the area to the left here. So a couple of ways of doing that. One way is we know that there's two of these 0.4678. So I can come down here and go equals, and we can go 2 times, and this is going to be B7. So if we do 2 times B7, that should double that for us. Now, if we go 1 minus that, so if we say equals 1 minus B8, that gives me this 0.0064. But notice how that's shared among these two areas here. So I actually got to take half of that to get the area to the left of this one over here, since this 0.064 represents the two unshaded areas. So if I did equals, let's see if we can type in this B9. If we divide that by 2, that should cut it in half for us at this 0.0322. So now I can actually find the z-score. So to find the z-score, I can use the inverse normal, or here it's got called in normal inverse. So if I equals, if I start typing norm, N-O-R-M, notice that norm inverse will actually find my z-score. So what we pick up on is the probability we need is actually this 0.0322. And again, I could type it in, or I could use BT in there if I wanted to. I've already got that in there, so we'll do that. Then my mean was 0 since these are z-scores, and the standard deviation was 1. If we close that off, that'll give me then this negative 1.84. Now, z-scores are actually symmetric with respect to the mean. So if this is going to be a negative 1.85, if you will, then the other one's going to be a positive 1.85. So I actually don't have to find it. I can use symmetry to get the second z-score in that. So once I find the left z-score, I can then use that to find the right z-score. So next question is kind of a word problem. So the red blood cells counts in millions of cells per microliter for a population of male adults can be approximated by a normal distribution with a mean of 5.9 million cells per microliter and a standard deviation of 0.5 cells per microliter. What's the maximum red blood cell count that can be in the top 22% of the counts? So again, if I kind of draw this out a little bit, so here's well, actually, we don't have z-scores this time. So the mean actually is 5.9. And then we have this 0.5 is your standard deviation. So 5.9 plus 0.5 would be is that 6.4. Then if I add another 0.5, it's going to be 6.9. Then another 0.5 would be then 7.4. Then if you go this way, that's going to be what? If I subtract 0.5, that's going to be 5.4. Then if I subtract 0.5 again, that's going to be what? Negative. These are negative 5.4. I'm sorry. No, these are not negative. 5.4 because we're not dealing with z-scores. We're dealing with the actual x values. So this would then be 4.9. Then if I subtract again, that's going to be a negative 4, I'm sorry, positive 4.4. So 4.4 plus 0.5 is 4.9, plus 0.5 is 5.4, plus 0.5 is 5.9. So if I draw my normal distribution curve, it's going to kind of take on this look here. Now the question is, what's the minimum blood cell count at the top 22%? So the top 22% is somewhere over here. So notice that if this is 50%, 22% is going to be probably about in this region here, if we're kind of making a judgment call at that. So what I'm looking for is the X value located here. So the top 22% means 22 or higher. So I'm looking for this minimum value for X. So since they gave us the top, notice that to do this, we actually need the area to the left. So we need to find the other side of the area of the curve. We need to find this side. So I have to subtract that. So if I go equals, and I can go 1 minus, and this would be what? B15, if you will. That'll give me the 0.78. So let me get rid of this here. I don't think that's right. So what I could do now, though, to find the X value is I now have my probability, and I have my mean of 5.9 and my standard deviation of 0.5. So we actually can find X here. We don't have to convert this to z-scores. So if I equals and do norm dot inverse, Notice the probability would be the 0.78, which would be the C15, if you will. Or I could just type in 0.78 there. The mean was the 5.9, which is B16. And then the standard deviation is the 0.5. So that would be the B17. And if I close out the parenthesis there, we have those going on. So it should actually give me my X value, which would then be 6.28, or this turns into 6.29 million. So this is going to be 6.9, I'm sorry, 6.29 million cells per microliter. That's a lot of cells. So 6.29 million cells per microliter. So part B says, what's the maximum red blood cell count for the bottom 13%? So the bottom 13%, if I draw that out, you can see my drawing's not quite right there based on that. So it's hard to do percentages there because I kind of wrote it out. So my drawing wasn't perfect there. So let's just draw the normal distribution curve and not get into all the numbers there. So this time says the bottom 13%. So the bottom 13% means the area under the curve is going to be to the left of this 13%. So this 13% is going to be here. So the 13% is going to be our highest value. So what's the maximum red blood count? We're actually looking for this X value located here. So notice how here we already have the area to the left. So I can actually find the X value here by using inverse norm, or here it actually says norm inverse. I'm so used to using the calculator. So notice how we have the standard deviation is, I'm sorry, the probability is 0.13. The mean is the 5.9, and the standard deviation is 0.5. So if I click on those fields, it'll just type those in for me. I don't have to actually even type. Keep learning in Excel what you can and can't do here. So if I hit enter, that'd give me my X value there, my maximum. So if I round to two decimal places, it looks like we're going to be like 5.34. So 5.34 million cells per microliter. So that's how we can use Excel to do this. But notice how, again, I think just like the calculator, we have to have the area to the left to make these all work.